All right, guys, let's get started. So let's take a look at Brightspace. We got section 2, table of contents. Okay, and I'm recording right now. All right, so we're gonna get, oh, you guys can't see, right? All right, so we are now, you guys should be able to see now. All right, just a few reminders. We have exam 1 a week from today. Okay, so don't forget about that. Exam 1, it'll be either the first half or the second half of the course. Okay. All right. So far, so today, let's take a look at Brightspace. So we've covered, guys, there, intro, word problems, tensor operations, baby GPT. You have your homework assignment. Last week I gave you these notes and the paper, things like that to read. I haven't assigned the GPT homework yet, just homework 2, but homework 1 has been assigned, and you guys are collecting text data for your next step, which is to train a GPT. All right, so if you look, we've got exam 1, and then, we're moving. So the course, the way that I did, oh yeah, I'm sorry. Yeah, the exam is going to be in here. Yes, you need to come to class for the. Remember, it's closed notes, but you're allowed a cheat sheet, an 8.5 by 11 page. You can write whatever you want, both sides. Any questions on that? All right, so far, so the class is divided in like 3 thirds, right? So the first third has been so far tensor operations, which all pretty much tie to a GPT and large language models. So we haven't really looked at an algorithm until today, right? A complete algorithm. So everything, I broke up the GPT into just different tensor operations, but they were all independent. If you remember, the common theme was that I always created the data from, it was random, right? So just random data, we just needed the tensors to make. But today that's going to change. So today we are actually going to use data, and we're going to bring all the tensor operations together to have a complete GPT. And it's no longer the baby GPT. That was kind of just a super simplified version of it. This is now the actual GPT, like, pretty close to the architecture of ChatGPT, for instance. That's not a mystery, right? So the algorithm itself is not a mystery at all. All right, so that's where, and we should be able actually in the first half to get through most of it because you guys already know the tensor operations, right? So everything that you see in there is like, okay, that's the attention mechanism, or that's this or that. So putting it together should be easier. There's a few additional tricks that have to be implemented. Just there are more coding tricks than anything else to bring things together efficiently. So I'll talk about that. And then during the second half of today, we will hopefully train the GPT and be able to ask it some questions, right? So obviously it's not going to be that great because I'm only going to train it on the adventures of Huckleberry Finn. So that's going to be my data set that I'm going to use. So we'll cover all of that. So today we'll be taking text and converting it to integers, right? So as I said, this is in fact now your first algorithm, whereas before everything has just been tensor operations. All right, so the things that I will need for this, so I'm going to go to the links. You can click on this link for the code. If you remember, we've covered every single Jupyter notebook in here except for this one, Scratch HuckFin, and here is also the data for it, huckfin.txt. Okay, so this is the script that I will go through today, and we're going to, basically put it together and train your full GPT. And this is actually the code that you will use for homework 2. Okay, so to train your model. So I'm going to use Colab, and remember that Colab needs it can give you a GPU. For the first half, I'm not going to use a GPU because it's just mostly me going over the code that would take too long and not really use up that GPU. But during the second half, when we're training the model, we can use a GPU. Yes, go ahead.
Is there a link somewhere that will help if you want it?
Oh, you want to do it locally? You do it with Anaconda.
Okay.
Have you ever used Anaconda?
I've not.
No one has asked me that question. Like Colab is so much easier and so that everyone just prefers to use Colab. But if you want, yeah, if you want me to just remind me at the end of class today, leave a few minutes and I can show you that. It's easy, but you have to install things. And if you have a GPU at home, then you have to install the CUDA libraries too, which is not hard in PyTorch in particular, but couple of steps. Yeah. Yeah, but I'm using Colab. It's just, pretty easy. All right. Any other questions, guys? All right, so I definitely want to get through this because I want to finish this topic, okay? So that's why I'm not going to demo what you requested right now. I just want to bring this together because we are finishing this topic today, technically, and moving on to the second third of the semester, which is more like regression types of things. And then the third is more like, yeah, I meant the second third. And then the third is more like image things. Okay, so let's go ahead. So I need to do Colab, which is what I need. All right, so we've used Colab before in this course, and somewhere over here. I'm gonna add a few code segments here. If you remember, we need to use to load our data, we need to use Google Drive. So I have my Google Drive. I'm gonna mount it. And I already downloaded the file. So what you can do is you can go to that link that I provided here, and you can download HuckFin, right? Just so that you can kind of replicate the results that I have. You see the tone of it, things like that. So you can download this file and just put it in your Google Drive, and that should be it. So I already took care of those steps, and it should be here in my drive. If I go over here somewhere, there it is. So huckfin.txt, right? So this is the book. One other thing you might want to do is you click on these little dots here and you can copy the path, and that's going to be very useful so that we can reference it from the code and that way are able to use it. Does that make sense? So we'll be using the file from almost the very beginning, okay? So remember today we're bringing together all the tensor operations that we have studied so far, which were relevant to LLMs, but actually you can apply them to anything related to PyTorch, right? So the same ideas. And the 107 operations and so on that we've talked about. So I've done this, so now I can go to scratch HuckFin, okay? I'm gonna need some libraries, which are the familiar ones, Torch, etc., for this to work. So notice Torch, Torch NumPy, Torch NN, which we will learn something new today, maybe for some of you. So whenever we develop algorithms with PyTorch, deep learning algorithms, we want to use an object-oriented approach, right? So I'm sure you guys have taken some kind of object-oriented programming course, so you know what I'm talking about, classes and all that. That just makes life easier. Otherwise, writing the code for this would be just, impossible. And everything in deep learning today is encapsulation. So what that means is the underlying is still PyTorch and the same code. But as you see these companies like Hugging Face and whatever, what do you think they are? All they are is encapsulation companies. They take PyTorch code, write their own function, encapsulate it. They keep doing that over and over and over. And it's easier to use their encapsulation than write 100 lines of code, right? Because but also it's what they've done only works for certain things. You lose a little bit of flexibility, but it makes life easier. So anyway, we will ourselves do that today, but by just creating classes. So I need to show you how that works. The beauty of that is, like I said, a lot of things, when you see them the first time, it seems very new, but as we go in the semester, you see that it's extremely repetitive, and we're always doing the same thing. All right, so we will use class inheritance, which I'm sure you've heard about. So essentially, you create your class, but that class inherits properties of another class, and that's going to be the NN class. So in PyTorch, the NN class does a lot of the heavy lifting for architectures. So we just use it for that purpose. And then from functional F, we will use this for softmax functions, ReLU functions, all these functions that we will be using to add, various things that we need to do, nonlinearities, etc. Okay, and so we will take a look at that. All right, so I'm going to load the libraries. Okay, so you can see the check mark is good there. Then I'm going to have some variables here, and these variables should be familiar to you already because we've been discussing them in the tensor operations, but I'm still going to state what they mean. So the first one is just, for torch, we want to set a seed of the randomization. Then we have this parameter device. So remember that we will be using CPU or GPU. Like today in the first half, I'm mainly using the CPU. In the second half, I will want to use the GPU. The beauty of PyTorch code is that it's written almost so that you can just change a parameter and all the code still works. So whether you're using CPU or GPU, everything should work, right? So this is usually, if you don't have access to a GPU or if that's going to be expensive, you don't want to rent a GPU until you absolutely need to use it. So in this case, this code actually automatically detects whether you're using CPU or GPU. So there's a command, torch CUDA is available. And if that's true, then you're going to be using CUDA, and that means something in PyTorch, else you're going to use CPU. So CPU, we all know what that means. CUDA stands for the CUDA library of NVIDIA. So, we're using NVIDIA GPUs here. And so there's a C library, right? It's like the drivers, if you think about it that way, right? So the drivers that we all need for hardware. So you're going to need for GPUs, this library to do machine learning. Okay, and that's what does it for you. All right, a few other parameters, and I'll hit the green button. So a few other parameters here. We have the block size. So you guys know, so remember, now GPTs, right? We're looking at in the transformer, the decoder part. So we've talked about this at length. We established that the key concept to understand was what a tensor was and the size of this tensor in LLMs. So it was batch size, comma, sequence length, comma, and then embedding, right? So this is the famous cube tensor that we keep transforming in the GPT. So block size is going to be 40. I'm going to go back now because this is a more realistic problem. I'm going to like real numbers. So 40 is the n tokens in a sequence, okay? This could be what? Words, if you want to think of it that way. Although in reality, we use tick token. Oh, we already covered tick token, so you guys know what I'm talking about. Remember, it's more like syllables, but they're syllables that are not created by humans. They're created by an algorithm, so they're called subwords, right? So they're very efficient. Or we can just use letters. So in this example, I want it to be so much from scratch that I didn't even want to use tick token either because that would have a layer of abstraction, right? That we wouldn't see exactly how it works. So instead, our tokens are going to be every letter, like the character, okay? And so that has a downside, but in terms of just understanding, it's pretty good. When you do your project, you should actually do with letters and with tick token and compare the two. And I think you will be like, you'll see a very surprising things that happens, okay? Does that make sense? All right. So block size is 40, batch size is 64. So that's the number. Remember, we give it 64 sentences, right? Of length 40. Maximum number of iterations is the number of times that we will do the training. And I need to talk about that because now we are doing training. So we have new parameters here. Eval interval is when you print results, like every 500 iterations or so, you want to print what the loss is doing. And the loss is going to be something that we need to learn about today because, we're doing training, so there's a few new terms. The learning rate, a lot of these things are things that we have to spend, learning rate, we have to spend like literally a class just on that. But for now, the way that you can understand it is, how all semester we've been creating these weight matrices, right? And they had random values. But I always said that those values were going to be updated by the learning process. So the learning rate controls by how much, if you will. So it's not like you calculate a value and that's the value that you change it by. Instead, think of it like in deep learning, all that deep learning gives you is whether you should increase or decrease. All those weights, though, but just zero in on one weight or one value, whatever it is, 0.3. So the whole stochastic gradient descent algorithm, what it tells you is, should I add or subtract from it? Do you guys see that? So if it's 0.03, okay, is it plus or minus in the update? Now the value you might imagine could be calculated, but instead of that, you can think of it as we just add that or subtract that. Do you guys see that? So that's essentially the idea. Questions on that? So that's what the learning rate is. Yes, so the learning rate is just, whenever we're updating the weights, let's imagine, let's go to the whiteboard. So we have a neural network, right? We have X times matrix multiplication weights, and that gives you some value Y. Over here, there's a bias also, and the bias is also parameters. So if we zoom in on this weights matrix, it might be something like this, like when we did 4x6 or something like that. You guys remember with Iris. So all these weights initially were random values, right? And all of our tensor operations. But now we're going to start thinking about training, and so we need to have new parameters. So just focus on one of these, like this one, right? So let's say this value, we zoom in on that, and that value is 0.02 for whatever reason, randomly, right? So essentially, what the learning rate does is we're going to need to update this value to be something else. So let's call this W, right? So now, what are we going to do? What does W become? Well, we're going to have 0.02, and then we need to update it. And that just means plus or minus, right? So we need to figure out if we do a plus or we do a minus. And that is determined actually by the algorithm called stochastic gradient descent, which we will cover in the second third of the semester. That's like the whole holy grail of this, like the whole magic, right? It works through calculus and things like that. So we will explore that. But that's what that gives you. So remember, you have a neural network. Data goes in, you have a prediction, you have the real value, you compare them, and you're trying to minimize that error. And that information is back propagated to update all the weights. And that's what that tells you here, whether you do a plus or a minus. Do you see that? And this is for every weight, by the way, for every weight. So it's got to be done. There's a way that because we have matrices, right? We have these matrix operations, is actually doable. Now, the learning rate is, well, when we're updating a value, we don't just have a plus or a minus. We also need to know the value that we are using there, adding or subtracting. So that is that learning rate that I just said, the learning rate, LR. So if it's, let's say a stochastic gradient descent comes back and it says, actually, oops, sorry, I meant to raise. Stochastic gradient descent comes back and it says, actually, it is a plus. So you're going to be adding. So then 0.02 plus, what was the learning rate? I think it was 0.003. So you just add that. And now the weight has been updated to 0.023. Do you guys see that? And that's the magic here. Then you now, with those weights, predict again, compare to the real, back propagate, decide if it's plus or minus, use that learning rate, and you keep doing that, but in an intelligent way, because stochastic gradient descent is very intelligent or very smart at telling you if it's plus or minus. And that's critical, right? Imagine if we just had to like randomly pick values, we'd never finish. But instead, it does a plus, and it's like, no, 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 actually, the other way. Let's do it, and it, and it considers everything together, the whole big picture. So anyway, that's the process. That's what the learning rate is. But we'll cover this in more detail later on when we discuss this optimization. Any other questions? All right, great. So that's what the learning rate is. Let's go back here. All right. So we talked about the learning rate. Eval iterations is another set, another like every so many iterations, evaluate the performance. It's another thing that we're going to print. And this is pretty important, vocab size. We've talked about this quite a lot, right? I said that probably for the real GPT, it's like 50,000 in vocabulary, subwords, which are like syllables, right? I gave the example of like iPhoning, right? So that's kind of that same idea. Then in some of the tensor operations, I did 1,000 subwords. But here, because I'm only using characters and numbers, like, and maybe a question mark or two, that, called special characters, right? Then in total, I have about 88. So that's going to be like 26 uppercase, 26 lowercase, a few digits, and so on. Does that make sense? So my vocabulary here is 88, I believe. Embedding size, this should be familiar to you, right? So this is the n, 40, 512, right? So creating that vector space with NN embedding from ID to 512 for every token, right? Everything is 512. Now this is new. N head. We have 8 attention heads. You guys should remember this, right? Remember that we pay attention, and I gave the example of just one attention head, but there's actually 8, which I gave the example that instead of having one person solve the problem, you give the problem to 8, and they all think about it, and then we would concatenate. Remember that? The concatenation of 8 heads, that's exactly what n head is. It's a parameter indicating head. N layer is the number of blocks. And for this one, I'm going to actually bring out one of the notes that I'm sure you guys have read already. If we go here to GPTs and homework, notes, this, right? You guys remember that we went over this graph. The baby GPT covered this part, but then it would only go into just one decoder layer. I only did the code for one decoder layer, and that decoder layer only had one head, if you remember. Now, every one of these blocks is going to have 8 heads. So there's 8 heads here, 8 heads here, 8 heads here, and there's going to be 6 blocks. But the nice thing about this is because n by 40 by 512 goes in and n by 40 by 512 comes out, then we just can keep running that through the next block and the next block and the next block. There's no problem, okay? And so that's essentially how it works. Then we're going to have our linear layer, and then finally, which this was also on the baby GPT, the linear layer and the final layer to predict the actual subword or token or however you want to call it, right? Characters in this case. Does that make sense, guys? So here we have the 6 because we are going to repeat this. And this is where those little programming tricks come in to do this pretty efficiently. Okay? So that, and dropout, don't worry about dropout. Just assume it's something we apply. We will study this later. It's not relevant to the architecture, and it's more relevant to like something else that we're going to be doing. But we'll leave that for another class, okay? But it's just a function you apply. All right, so I've established the parameters, so I assume that's good to go now. Then we're going to continue. Okay. As you can see, the next step is to read in the data. So this is relevant to your work for your project. Remember, you're going to have multiple books or multiple files. You'll need to figure out how to do that on your own. Okay, I'm only showing how to read in one file. Creating one massive file with all the books in the world, probably not a good idea, right? You want to read your data in batches somehow. And now the great thing about deep learning is when we're training the models, we do train in batches. So then it's, you grab a batch and another batch and so on. Okay. All right. So here we are. Let's read in. So this is where I need the full path actually. So I'm going to copy the path from my Google Drive. I'm going to put this in single quotes. So remember, I'm just going to train on the adventures of Huckleberry Finn. And this book I got from the Gutenberg Library, gutenberg.org. All right, so there we are. Okay, questions? So I have, I'm going to, this is the file. I'm going to just use basic Python things to read it. And I'm going to store it in the file text. So I'm just going to load the book in memory, and then I'm going to show you guys how we go from this to n by 40 by 512 for training. Okay, so that's essentially what should happen. So let's go ahead and read it. You can see it already read it in there. Okay. Oh, I don't know why. Has it been out all this time? No. Okay. Okay. All right, there we go. Okay, so I read the file in. I have it available. Okay, so now, I like to look at the data, just get a feel for it whenever I'm doing things. So here, the length. So this is actually a question I will ask you when you do your presentations for homework 2. I will ask you, this is a common thing you see in papers also. Papers will say, oh, we trained this model with 1 trillion tokens or whatever. That you see that a lot. And what they mean is this, this is a metric of how big your corpus was. This doesn't count how many unique subwords you had, but all the subwords. So if you have the 4 times, that's 4, right? And so all the words, so all the subwords. So in my case, I'm counting the letters because that's how I have made mine. Do you guys see that? So it'll be very useful for you to quantify how many tokens you use, because then I know, okay, if you tell me you use 3 books and you use 3 books, but maybe your books are like poems and your books are encyclopedias, right? So that's not very useful. What might be more useful if you tell me, the number of tokens. So it might, then you say, oh, mine had 1 million tokens and mine had 10,000 or something like that. Do you guys see that? So that's critical because more data is useful. Yes. That depends on how you tokenize it. The correct way is via tick token. Yes, that's the correct way to do it. So, guys, any questions? So letters, I'm using letters here for 2 reasons. One, to explain this from scratch, like literally no magical libraries or anything like that. That's one reason. But actually, also because I want you to see something very nice, right? So when you train with letters versus training with tick token, you will see a huge difference. And that's because when we use letters, we're giving the model too much opportunity to just make up things. And not just make up strange semantic things, but make up words that don't exist. It might say cat with 7 T's for some reason. Do you know what I mean? Why not? Because it can. But if you're using subwords, you wouldn't be able to do that so much because there is no CAT. There may be a CA and a T. Do you see that? So you have a little less limitation there. Got it? Yeah. So tick token is the way to go. I hope I said this when I gave that lecture. Tick token is based on an algorithm called BPE. It's quite of a complex algorithm if time permits at the end of the semester. But otherwise, I'm going to leave that one to you because it's not as critical as, you just use it. You know what I mean? And it's quite complex, actually. All right, so you have the tokens, right? So everyone understands that I will ask this question on your presentation. Okay? And I want to know who used the most data. I'd be very curious if. So how that worked and all that. Pardon? No, not really, not like that. But it's just a useful thing. I could say that if all of you used 1 million and then someone comes in with 10 trillion, they probably have a better model. Just because the scaling laws say with a GPT, more data, more GPUs, more architecture, better model. Quite simple. Yeah, go ahead. Yes. You can. I mean, you probably want to be efficient, but yeah, you can keep collecting data. Yeah. Yeah, that's logical. That's the point of the assignment actually is to show you the difficulties, right? You need data, you need GPUs actually. And it's not about the software or anything like that. All right, so we've done this part. So we can look, I want you guys to see the the tokens in this case. So you can see that there, all I'm doing is I'm using set, which is a way to grab unique characters in there, and then I create a list. So these are the letters. You can see there's uppercase P's and there's lowercase P's and a few special characters as well. There's actually very few numbers, but there's a few like 7 and 2 and something like that. Got it? So this is what we're going to be using. This is just from the book Huck Finn. Okay? So that's where it came from. So this is going to be our vocabulary. All right. So now let's do a few things. I'm going to now create an official variable called the characters, the chars. And that's where I'm going to store so from text, get the unique letters, create a list, and then sort them. Okay, and that's going to be the chars. And that's my vocabulary. So the next steps, I need to create an encoder and a decoder, right, just for this, called a tokenizer, so that we can do the conversion from ints to letters and then letters to ints. As you remember, the GPT only accepts ints. So we need to convert these letters to ints. Okay? All right, so we've got that completed. Okay, so if we look at the size, it's 65. This is pretty important for the dimensions, so we would want to get this one right. Otherwise, our model will break. So, but yeah, vocab size has been recorded, and it should be 65. I'm just going to print those two values here. All right, so I'm printing the size, and also I'm joining all these letters in a more readable way. This is not really helpful to the model. It's just for us to visualize. You can see there's actually 88. So I think I do have 88 at the top, but I sometimes in the code I have written 65. Okay, yeah. All right, but it should be correct, 88. All right, so that's done. Now comes like what you might think is the mapping, right? I'm just going to use for this example, tick token does this for you as I demoed in the previous class, but here I'm just using a simple dictionary to show you that we can do this manually. It's just not as great. Okay, so you can see there, I'm creating two dictionaries, string to integers and integers to strings. In NLP, this is very common. You always create these, what are called forward and reverse dictionaries. They're exactly the same thing, just flip. So one has an index of the number and the other one has the index of the word. And then you can look up the other one really quickly and efficiently. So you can see here, all I'm doing is I'm enumerating through the chars, and that's going to give me the position and the letter. and then I'm creating the dictionary. So you can see character to integer or integer to character. These two things are two separate dictionaries. Okay, and this is equivalent to tick token as I used it the last time. But we're doing it from scratch. All right, that's really great. So we can take a look at the dictionaries and see what's in there. You can see there, we've got, probably better to see it here. You can see we've got, you know, what is that? You know, $sign to 4 or the letter U to 74 versus when we're doing this in reverse, 74 to U. Okay, and just to return it more quickly. All right, so that's pretty good. Now an example of how to use this. So I'm going to use these lambda functions. Lambda functions are just an abstraction in Python. They're useful sometimes. Sometimes they're hard to understand, but essentially you do like function with this variable, and then you specify the logic. Okay, so here we give it an S, and then the logic says for C and S. So we just iterate through that string, in this case, letter by letter. Okay, and then what do we do with the C's? We insert it in string to integer so that that letter can be converted to the integer. And then you can see that here. So I'm going to use encode for the word ba, right? So sheep language. And I go over there, and now you can see I've got my integers from the dictionary. And there you go. Here now I'm almost getting, you know, let's say I have a sentence. I can convert that sentence into my sequence of integers. And now I'm starting to build my tensor. Got it? All right, so that's the encoding part. Now comes the decoding part. Same thing, I'm going to create a lambda function, okay? This one gets us input this letter L, and then I do for I and L in my list comprehension. I'm just iterating through all those integers, and I plug in that integer into my integer to string dictionary, and boom, I get my letter back. So if I give it 55, 54, 61, 61, and I run that, I get my word back. Got it? All right. So there we are. So this vocabulary the matrix, the embedding matrix for this is going to be 88 by 512, right? You should remember that. So we're going to be building that soon, but we need to look at a few other things. So the next step that we need to do is this one, very important. We're going to take the entire book and convert it into integer, because we can, right? Why leave it in strings if we can already take the whole thing and convert it into integers? So the whole Huckleberry Finn will now be encoded. So I'm going to do text encode. Notice I'm using integers here, and I'm going to convert it into a torch tensor. So it's going to be ready for us to operate on, and that's going to be the variable data. But you should understand that it's still the book, right? It's still the book from beginning to end. You know, Huckleberry Finn went to the river and something and something. It's just that the words have been replaced with the corresponding integers, or the letters actually in this case. Okay, so I run it, and there you are. You can see it's comma separated. And this actually would, whether you're using letters or tick token subwords, still going to look like this. Okay. Any questions on this? Right, strings are gone, right? So text is gone. It is all integers now. All right, so very good. So now let's go back over here. And here comes not let's say the hard part, but this is new and critical to understand. There's a lot going on here that might surprise you based on the way it's done. The first thing I'm going to do is just split that data into a train set and a test set. I'm going to leave a very small data set, 10% of the book, the last 10% of it, essentially. as test. And I'm going to take the first 90% of the book, let's say there's 10 chapters, or the first 9 chapters I'm going to use for training, the last chapter for testing. Okay. In this case, it's all language, so it shouldn't be a big issue. And plus, you would assume you'd have millions of books, so it wouldn't matter. All right. Here I'm just calculating where 90% is in terms of all those indices. And then you guys, of course, know this because you know slicing and all these things from doing the 110 problems, right? So I'm just going to slice this. And there you are. So now I'll be using trained data mostly, right? This is my train set that I'm going to be using. Okay, here comes this. This is one of the very important functions that we will be using in this GPT model. This does a lot. And so what I will do to describe it is I'm going to actually break it down into the different parts, but a lot is going on here. First, we just say, it's called get batch, by the way. So every time we want to train the model, we get a batch. Feed it to the model, get another batch, feed it to the model, and so on. So we just, split just determines if it's we're doing training or testing. Okay. Then after that, we're going to do this step here, and then this step here. These are two pretty important concepts of how you train a GPT that, like I said, might surprise you. Okay. The first one is essentially picking positions in the book randomly. Like if this is the whole book, it picks this position, this position, this position, that position, just randomly. So that's, the book goes from 1 to 1,000,000, right? So 101,000, 250,000, 307,000. And it's just whatever word is there, that's the starting point. Okay? Okay, that's one thing. And then these two lines here are actually what creates the data that is used for training and testing. Okay? So it's based on these initial IXs here. So before I demo this in the code, I'm going to go to the whiteboard, okay, and explain this. Let me run it yeah. All right, so let's go to the whiteboard just to because this is actually pretty important. Okay. So we have been looking at the GPT architecture, right? We've been looking at the GPT architecture. And that you guys know that whole architecture from beginning to end. What do you know about it? A tensor goes in, right? A tensor goes in and a tensor comes out, right? So essentially, this is the input and this is the output. Another way of saying is this is the prediction, right? So this is what it's predicting, speaking to you, right? You ask it a question. Okay, so another way of saying this is you ask it a question. Whoops. You ask it a question that goes there. It gives you an answer, comes out. Got it? All right. So that's when it's being used in inference. But how do we train it? And what is that function doing get batch? So imagine we have the book, The Adventures of Huckleberry Finn, right? And it's sentence, 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 So a whole bunch of sentences. So the IDX or the IX, whatever it was that we're using, is essentially telling you points in the book that it's picking, starting points, okay? And it says however many you want. So for instance, this is where batch matters. If you're doing 32 batches, right? It's 32 sentences, so it's 32 points that you pick, okay? Then after that, you know the size of the sentence that we're going to use for the GPT, which is 40, right? So then it grabs 40, 40, 40. 40. Does that make sense, guys? It's grabbing those chunks out of, yeah.
It's really not necessarily like a sentence, like you would imagine it in English. It doesn't necessarily start with capital. A chunk of.
It's a chunk, yeah. That's actually a chunk. The correct term might be chunk and not sentence. You are right. It's you know, the cat sleeps on the chair, right? IX is just where you start to get that chunk. So let's say that it said 3. Okay. 0, 1. Well, let's start at 1, 2, 3. So, and then the size is 4 because I don't have more words. So 4. If I'm using words. If I'm using subwords, then I have, then it would be somewhere in here. It just depends. If it's letters, 1, 2, 3, 4. So it would be that. Do you see that? Guys, everyone with me on this one? Pretty important. All right. So if you understand that, that's really great. Okay. So you select those randomly, by the way, randomly. So you're here counting on the fact that you're going to do this millions of times. Do you see that? Because it's random. You don't have any like structure on how you're doing this. So this is where, again, massive amounts of data are great, right? Because imagine now you can start in all points and grab chunks of 40 and all like that. Okay. All right. So once that's done, let's say we did 32 and they're chunks of 40. So now we've created our tensor that has 32 because there were 32 starting points. Each one is of size 40, which is a chunk, and they're already IDs, right? They're already integers. So this just looks like 3, 7, 5, 9, 2, ... Do you see how this looks exactly like the starting points that we had initially when we were creating our random tensors? Everyone with me on that one? Any questions? Yeah. You're gonna have 32 because the problem is you're gonna have millions overall over time, but you're really gonna grab 32 or 64, feed it to the model, then 32, 64, feed it to the model. Yeah, each batch would have 32. 32 is, so remember the tensor takes n by 40 by 512. So n was, if n is 32, it meant 32 sentences.
Yeah.
64 is in our code. Yeah, specifically our code is actually 64. Yeah, so we are grabbing 64 sentences, but randomly, okay? And from anywhere, actually. The only thing is they have to be sequences. That is pretty important, okay? Any other questions, guys? Is it making sense there? You go ahead. Yes. Yes, because look at what I was saying. If you grab a million sentences, that's too much memory, right? To feed into the transformer. And so that's not going to be efficient. All machine learning, all deep learning works like this, as we will see. You give data in batches. It's like literally built around that. Because you can't, even if you think, okay, I give it 32 images, but that's not a lot. Yeah, it's not a lot yet. But in the CNN or in the stable diffusion or whatever it is, it becomes massive because of all the things that we're doing in parallel. Okay, so that's actually the point. You have to take, yes, but you can't even give a book in one batch. It's got to be just from that book, you select some sentences. So you have to think of a strategy to do that efficiently. What you can't do is take 1 million books and create one file. That may not work. That's too big. I mean, it's too big, right? In my case, I have Huck Finn. I could have had 10 books and that would be fine. Concatenate them and do this out of that. And then for a while, and then throw that away and bring another 10 books, concatenate it, randomly pick a few of those for a while, do a whole batch because you want it to get some coverage. And then once you've gotten the coverage, you can go back to the books that you threw away and run another pass. But it just depends. You have to have strategies for this. Or a cluster of 100,000 GPUs like Meta and OpenAI can do. Do you see that? So these are the downsides that we can't deal with yet in people that only have one GPU. Any other questions? All right, good. So you can see, right? So that IX just gives me the starting points, and then I'm just gonna slice out some data, right, of a specific size 40. Okay. Now the other insightful thing is we need to have actually not just the sentence that goes in, but what comes out, right? So if I have 32 of these, I have, let me move to another. So if I went through the book and I created a batch of 32 by 40, okay, that's what I'm feeding to the GPT, but what comes out of it needs to be compared to something, right? And so the way that it works is I have the GPT, and this is X that goes in here, right? X, so it goes in there. But we need the model then is going to learn to predict something. Let's call it Y hat. But during training, it needs to compare that Y hat to a real Y to learn, right? Where is that one coming from? As it turns out, it is very similar to this X. It's going to be a 32 by 40, but, and we're going to call it Y, but the difference is that this sentence is the same as this sentence, except that they are shifted by 1. So I grab a sentence as input, and that's my same sentence as output, but shifted by 1. Yeah, by one token. So why do we do that? So let's think of the architecture of the and this is like fundamental. If you understand this, like, a lot of things will make sense to you. If I have a GPT, you can think of it as the cat is sleeping. Huh?
No.
Yeah, I should use another. I think these things are just if I don't use these sentences, then I forget everything. All right, so then over here, what you want is that the model should predict if it sees the cat, if it sees the cat is, if it sees the cat is sleeping, and here's the magic. This is not in the input on. Do you guys understand this? This is how it works. This is the magic. So you had asked me one question the other day about in the attention mechanism, the mask, that trill. You were confused with that concept because you were also trying to answer this. And that's what was confusing you. So what I should have said then was that the mask, as we were doing it, is not all that controls the learning. That mask was just there to calculate those little values, to restrict what one word can look at other words, right? So it can only look at the words that are there in that trill. But that's all it does. The actual learning is controlled by this. Okay? So this is because if you notice here, so when we grab so we are obviously going to grab a sentence, the cat is sleeping. On. That's actually the sentence we grab. Sorry, I should say on. So we are grabbing this sentence, right? And then once we grab it, we are going to convert this into X. Well, actually, I should. We're going to convert this into X and also Y. Do you see? And how do we do that? Is the exact same sentence, except that we pop the word, we pop the word on from this one, and we pop the word the from this one. So the extreme, and that's the same as shifting. Do you see that? So they have the same size, but they are shifted by one. Do you guys understand? This is exactly how it works. We do this because that's what the model is going to learn. The model is going to learn to predict the next word. We really care about this one. You see that in that one is only going to be present there, but it also looks at the whole sequence, you see, because they're all connected. Yeah. No, right. If you don't shift it, that's not the objective of a GPT. The GPT is just learning the next word. This is how it learns it. This whole mechanism just to do that. Okay. And so, yeah, so did you guys understand, right? So we pop on for Y and we pop the for X. Sorry, we pop on for X and we pop the for Y, which is essentially shifting by one. Okay. And now that they're shifted by one, the model is going to do this. When we do, now you might say, but if I give it the cat is sleeping, this is not useful because I already knew that, right? And you're right. It's not. What matters is on, right? So when you're doing training, it does matter because in training, it's going to compare this, this is actually Y, or this is Y real. It's going to compare it with Y pred, whatever it predicted for every word. So it's gonna, it's not just that you're optimizing based on this. You could, but it's probably more efficient that, it got this one right, but it got this one wrong. That's not the model you want. You want the model that gets this one right and this one right and this one right and this one right. You see how it's a little bit better that way by getting all of those correctly. Okay? So that's exactly what's happening. When we do inference, we just think of it as applying the model multiple times to predict one word at a time. So for instance, you give it an input, right? You give the model an input, whatever it is. That goes in, it produces an output, right? And you just care about that last predicted value. Do you see that? And then think of it as you just attach that little predicted value and and you pop off that little value. And then when you do another prediction, it's got the last part. So you just add that at the end and you pop off another one. You see how it's just concatenating whatever it's predicting to the sentence, dropping off the rest, and it just can do that forever. Like it can literally do that forever. That's why a GPT can tell you a whole book. If you ask it. Now go ask ChatGPT to write you a book. It won't, first of all, because of GPU things and also performance would go down. But it can certainly, that's why it gives you so much text, right? Because and amazingly, people never expected that it would be so smart and it would do all the things that it does, right? But essentially, that's how it's working. You're just adding. Okay. We will see that I do have a function called the generate function. We will look at that, but that's the last thing we will cover. Okay. First, we need to do the training, etc. Make sense? Yeah. So just think about it. We shifted, you'll see it in the code, and then you provide things, and then although we are training to learn all these words, really the new word, as you can see, if I say, explain to me quantum computing, it's going to say quantum computing is and entanglement. So that's going to be the key word that it learns, right? And that wasn't in there. All right. Okay. So we've done that. So I think that is the logic. So we can go back to the code now. Yeah. This is the code. So now you should be able to really quickly visualize this, right? Notice what I do here, torch rand int. The data goes farthest length minus the block, because if we pick one, we need to have enough for a block. So that's what's being done here. And this is just the batch size. So, 4 batches, 32 batches, etc. I'll print these in a sec. So now I have my indices that I want to pick. Now notice over here what happens. I'm going to create my X and my Y, which is the thing that I said was shifted, right? So I say for I and IX. What does that mean? Every position here in the book, here in the book, here in the book, here in the book. That's my starting point. Data, you guys know, is the whole book that I just collected. So I go to position, let's say 20, and I slice from 20 to 20 plus block size. Block size is 40, so that should go from 20 to 60. Boom. I just grab my sentence, X, right? Now I want my sentence that is shifted. So what do I do there? I do the exact same thing if you look at the code, except that it was position starting point is 20, 20 plus 1, shifted by 1, and then 20 plus 1 plus block size is 61. So X is from 20 to 60, and Y is from 21 to 61. Make sense? And I'm doing it on a batch basis. And after that, this is just PyTorch's way of saying load this to the device, whether you're using a CPU or a GPU. Things like the model and the data, we always want to load to the device to be faster, right? This is something, there's no science here. Just learn how to use it by looking at a lot of code, okay? All right, so now we have more importantly, we have our function. To be a little bit more concrete here, I'll provide some examples just to kind of give you some idea. So we can explore this one. This is not relevant to your homework. You can actually remove this later. But I'm going to assume a simplified thing. A batch size of 4 and a block size of 16 instead of 40, just so it's easier to visualize. And I'm going to create my IX. Select the random starting points for just these 4 sentences. Because it's a batch of 4, it means it's 4 sentences. There they are. Those are my 4 starting positions, okay? Now, what? Are you using the same seed as I am? Yeah, so the seed is used for that, so that we can all replicate results. If you wanna, you have to, yeah, you have to use a random seed. All right, so this is useful sometimes if you're comparing a model with one approach and you want to compare that same data after you do a fix, you need to have a fixed seed. Otherwise, it might be better, but it's not because of the model improvement. It's because you just picked another data set from the population. All right, so now that I've done this, I'm going to go ahead and just show at those index positions what the value is. So for whatever reason, the values are 1, 59, 1, and 1. Whatever those are. Remember, those are IDs that match to letters, right? So it could be T, for instance. Is that 1 or something? I don't know. You can look it up in the dictionary or double quotes or something. All right, so once you have that, notice what I'm going to do here is from that get batch function, I'm getting these parts, right? So I broke out these 2 X and Y parts just so that we can see them. So it's gonna do that. Gonna grab the indices, right? And shift them. And then we're gonna contrast X and Y. And you can see that there. So if you notice carefully, right, you know that X and Y, right? So whenever you train the GPT, this goes in The model predicts, and whatever it predicts will have the same shape, and then you compare it to the y. Got it? So this is 4 by 16, right? So the GPT gets this, 4 by 16. It predicts a tensor that is 4 by 16. And that tensor that is 4 by 16 that was predicted is compared to this tensor, which is 4 by 16. You minimize that error, that's it. It's the whole game right there. It's nothing more. I can leave right now. But you know what I mean. That's essentially what's happening. So you need to understand this idea. So if you look carefully for the first sentence, it is 145.61. Notice down here it shifted to 45.61.54. If we look at the end here, it is 82.65.65. If we look down here, it's 82.65.65.1. This is the thing that is new, the term that is being predicted. Okay? All right. So yeah. So if you understand this function then, and you understood the tensor operations, you're like almost there. So now, yeah, we're done. That's it. So that's the explanation of get batch. Okay. There is this function that we're going to use. I will explain this one later because this is not really relevant either to training or to architecture. It is just an estimate loss. It's just something that we're going to be using to measure performance. So it's like a metric. So this, I'm going to skip for now, and we can come back to it later. But we are now ready. If you look over here, what comes next is the NN architectures. So we are essentially right there. To now we're going to put together everything that we've learned all semester, the attention, operations, everything else that we've done, and we're going to just put it together into one single sequence. All right. Going back to this one, I'm going to have my 6 blocks now. Every block is going to have 8 heads and all of that. Okay. So that's what we're going to proceed. So instead of like going, I'm not just going to throw these architectures like this. Instead, what I'm going to do is I'm going to start, if you notice, I should say, there's, and then, class head, class feed forward, multi-head attention, block, and GPT model. GPT model is the primary class. So I'm going to start here. This is the one that is mostly like the baby GPT from beginning to end, but just keep in mind, it's calling the other classes. Okay. So I'm going to start here. And if you notice after that, that's it. All I do is I instantiate the model. I create this thing called an optimizer, which we will discuss, and boom, training happens here. At this point, the model's trained and we can ask it questions. Okay, so we're almost there and we should be able to get to this today. But we're going to focus our attention now on this, the GPT model. Okay, so I'm going to grab this class. And I have to make a pause here to let you know a few things about this class, okay? Which is pretty important. So, okay. So first of all, if you notice, this class and all classes going forward this semester are going to look exactly like this. All right. Whenever we build architecture, we want to use an object-oriented approach. So we're going to define, use the class name, give it a name. So in this case, GPT model. It's going to inherit that NN from the top from Torch, and then dot module. This is the class inheritance, right? So, this allows us to create a very complete class just by inheriting from that parent class. Inside, it's going to always have a minimum of 2 functions, although this one has 3 functions. Generative models have a 3rd function, okay? But where the generative function just calls the forward function. That's essentially what it is. So essentially, every one of these needs to have 2 functions inside. The first one, this one, is called init, the init class. It's got 2 underscores in the front, 2 underscores in the back, and that's What is it in object-oriented programming? The constructor, right? So if you remember that, so that's essentially what it is, right? But it's the initialization function or whatever. And the second one is the forward function. And this is actually in it, you just initialize things. In forward is where you actually build the architecture that defines X goes in, all of this happens, and output comes out. Do you guys see that? And this is something that is not just exclusive to LLMs, we will use all semester. But it's actually not a bug, it's a feature. It's not your enemy, it's actually your friend. Is this template that allows you to think very clearly. Okay, I do, class, init, this goes here, forward, boom. I get it. So it's actually a very simplified way of doing things. Okay? So I'll do in the whiteboard a very simple example of this. But this is something that, put on your cheat sheet, right? I'm not going to ask you questions about this on the exam, but what I mean is it's so important that you're going to see it a lot. So class, the name, and then dot module, which is the thing you're inheriting almost always, colon, and then you have def, init, right? And all that information that goes in here, which is going to vary, and then def forward. And, the actual neural network, and usually there's a return here, and that's the prediction, okay? Almost all of it is going to be in this format. Okay, and then this function can have many other, it's a class like any other, so you could add 15 more functions if you wanted to. But you don't want to add things that are not necessary. But these need to be there, okay? Because this NN module works with this structure, so you need to be consistent. Okay, any questions about this? All right, great. So now that we've discussed that, okay, we can go back to our, right? So class. So we can't run this yet because obviously this calls a lot of things, okay? But we can start to go through it. Now, because we've done all the tensor operations, a lot of these things should already be familiar to you, okay? That's the reality. All right, so we start here, init, right? So you always have this function, like always. And that's just to initialize the inherited class, so the super init and everything else. So just assume it just always goes there. Remember, here we're just declaring things. So these two lines of code that you're seeing here should absolutely be familiar to you. What are they? They are the way that we convert n comma 40 into n comma 40 comma 512, right? But remember that we would do that twice, one for the semantic embeddings and one for the positional embeddings. So we covered this already, right? When we did the embedding. So we used the construct in an embedding, and notice that we initialize this as a vocab size to n embedding. So the vocab size here is 88, and n embedding is 512. I know I wrote 65 here, but do you see that? And then for positional encoding, positional embedding, we did the same. What was it? Block size is what? 40. And this is 512, so it was a 40 by 512, and that allows us to run our data through it so that we can create two tensors, one for the semantic embedding, one for the positional embedding. This is from previous classes. We have this amazing magical thing here. All right, so this is actually one of those programming tricks, right, that takes care of something pretty great. So I'll talk about this when we come back from the break, but just keep in mind that this is, for now, I will say that this is where we create these 6 decoder layers. So you see 1, 2, 3, 4, 5, 6. All of that neural network that's very deep is just created with these 3 lines of code. All right, so we'll discuss that when we come back. This is just a normalization layer. This is everywhere in neural networks. Remember I said to you guys that neural networks, right, like values that are between -1 and 1 or 0 to 1 anywhere. So you're always, at layers, hidden layer 6 or block 3, and you run whatever that tensor is through a normalization, or you run it through a dropout, or so these are these kinds of functions. And then if you notice, this last layer here is the last layer, the linear layer here, linear layer that produces this output, okay? So that one we've also discussed in the baby GPT. You guys remember that it would go from 512 to vocab size. Why? Because it was predicting that token. Do you remember? So that shifted on, right? So we need to predict that one. And so that's what this does. So that's the last layer of the baby GPT. Make sense? Any questions so far? All right, so it is 7:49, right? 7:50. We started at 6:30, 7:30. Yeah, so it's been an hour and 20 minutes. Let's take a 10-minute break. We will come back to this part and then just put together the whole thing and train it. Okay? And we should be done with the LLM. All right, so let's take a 10-minute break until 8 o'clock.